All right, hey y'all. We're going to be doing another set of lessons today. I'm going to combine two into one video because the first one is more of a discussion than anything. We're going to talk about a term called asymptotes. It's just going to be an informal look at them. You'll have seen them in the you should have naturally came to the conclusion that these things do exist. After that, we're going to talk a little bit about dividing one polynomial by another, and you'll see how that can actually be helpful for your individual work this evening. So let's start off with the horizontal asymptotes. So this was really going off of the Yinsun's copy on what her function looked like at the important parts, but at the end points, or where it was going off towards infinity, she actually had some idea of what was going on. With this limited information, she was able to deduce that it might be a few, but we can actually see that we can make some assumptions and ideas about our functions just looking at those extreme values. So if you are looking at a horizontal asymptote, well, let's take a look at some examples. So say we're given a rational function such as f of x equals 1 over x. What we would get is actually a sketch that looks like so. So our horizontal asymptote is saying as we're looking farther and farther in this direction, what y value does what y value do we tend to approach as we're going really far negative or really far positive? So with the horizontal asymptote, such as this one right here, notice how this kind of just skims across our x-axis. As x approaches infinity or goes to positive and negative infinity, what does our y value approach? So the way we saw this with Yinsun's is that we basically canceled out the middle. We're looking at the function and we're saying, okay, well, on this end, it looks like it's flattening out towards y equals 0. Same with this end right here. Doesn't matter what the important stuff is, it matters where our end points are going. Towards infinity, x approaches. So let me clarify that. This arrow right here means approaches infinity. Our y approaches 0. And as x approaches negative infinity, y also approaches 0, just from below, right? So this is what our endpoint is telling us, and if you can draw a horizontal dashed line that you know your function is approaching in both ways, we can actually see that, that there is one horizontal asymptote. We can have two asymptotes. At the same time. And so what that might look like, I'm just doing a rough sketch. Might be a function that looks like this, where we have what's called a logistic curve. So here, notice that we have two asymptotes going on. One is when x is approaching infinity. And notice how it flattens out right here to this above line. So we could say as x approaches infinity, maybe our y, let's call this +1 and -1 for the sake of clarity. So this hash is going to be 1, this one down here is -1. As x goes towards infinity, we're finding that our y actually goes 1. And now, as it approaches -infinity, or we're going backwards really, really far, notice value is approaching this -1 value. And then finally, might be one where it doesn't quite, it might pass through our asymptote every single time. So passing could be a function that looks like this. We have our x and we have our y, and our graph might drop down, go above, and then it starts straddling this x value, or this x-axis. And in the same way, it does the same thing over here. Something like that. So if we're looking at something like this, then we can actually see that it's going back and forth between the x-axis, but at the end of the day, we're still approaching that y equals 0 asymptote as our x goes towards +infinity and as our x goes towards -infinity. So, if we wanted to talk about this one, we'd show our notation like this, and as x approaches -infinity, our y also approaches 0. So this is x approaching -infinity up here. So all you have to see with a horizontal asymptote is that it's a specific y value that our function is approaching as our x values get really big, both positively and negatively. I'm just going to touch on a slant. And so when we're talking about slant asymptotes, that's kind of when our approaching value isn't a certain x value, but it depends on more or less a linear equation. So these things can cross. Just having a sketch of what a slant asymptote might look like. We could have two slants such as this, and we might actually have a function that actually gives us, and I will look up a great example. I want this to be really clear because sometimes this stuff can be pretty confusing. Okay. So one of our asymptotes could actually look like this, where we have an equation that goes like so, and then we can edit this, and then maybe our next part of our function looks like this. So the important part to look at, this is a little sloppy, but notice how this end and this end, as we're looking at those extremes, tend to approach a slanted part from both sides. Usually we would show this as, instead of just saying x approaches our value, y value approaches some value, we could say as x approaches infinity, like so, y might be approaching x. Or it's saying, okay, well, we know that y equals x gives us a linear equation where the rise is the same as the run. Infinity about the interesting part, we see that it actually slants. This is something that you will have seen in your lesson activity today. So that's horizontal asymptotes. That's the idea behind them, as well as slant asymptotes. The next thing I'm going to do is polynomial division. So lesson part 2, polynomial division. So polynomial division, not as bad as it looks. I'm just going to do this by example, give you 2 examples. That should be a good amount to get you understanding what we mean by polynomial division, as well as to figure this stuff out. So we're going to use this thing called an area model. We're going to start off with the example f of x equal to x to the 4th minus 6x cubed plus 18x minus 1, all divided by x minus 2. So in order to set up this thing to do polynomial long division, we need to think about the area of a box. So if we're looking at the area, we know that we can find the amount of stuff inside by taking a look at our length and our width. So maybe we have x and 3. So if we want to find the area, it's just x. Now let's say we have another example where we might have the area of our box being equal to 3x squared, but we only know that this length is equal to 3x. So we kind of have to backtrack to figure out, okay, well, 3x times a value gives us 3x squared. So if we wanted to find the other dimension, we would just have to fill in the blanks. 3x times some value is going to be 3x squared, so we know that has to be x, because 3x times x is 3x squared. So we're going to use this idea to kind of fill in a rectangle. This is called the area model. Pretty helpful. It's a good way to start thinking about algebra, thinking about multiplication in general, because it gives you another kind of more tangible way of looking at these types of examples. So in here, we are going to make this x minus 2 our, so if this is length and this is width, this is going to be our length of our box. So we can actually put x minus 2, and that's going to be our length. So what we're doing here is trying to figure out how to fill in this box, so we're following this rule right here, or following this polynomial right here. X to the 4th minus 6x cubed plus 18x minus 1. So we're looking at this thing and we're saying, okay, I have an x. I know that I need to start off with an x to the 4th. So my first question I'm asking myself is, well, if I have an x and I have an x to the 4th, and these are all little boxes, this width have to be in order to make this little box have an area of x to the 4th. Well, we know that if we have an x, we need to multiply by an x cubed to get to x to the 4th, so we're good to go there. Now what we're going to do is bring this down to here. So if this is an x cubed, we know that this length is an x cubed. So if we're going to fill in this part, we know that it's going to be negative 2 times x cubed, or negative 2x cubed. So next step, and I'm even going to write this down I'm going to write down the general procedure here. So 1, find the missing width. And so that's going to be this first part right here. Step 2, use the found width to calculate the missing area. So we took our x cubed. We know that this length, these two lengths are going to be this missing bottom value. We just multiply our length times our width. So the last thing we need to do is figure out how many x cubes we need to add to this so that we get the negative 6x cubed right here. So we're more or less saying, all right, well, if we have our negative 2x cubed, what do we have to add to it to make it negative 6x cubed? Well, in this case, we'd have to subtract 4. So we know that this mystery value is going to be a negative 4x cubed. And we can actually place this as our new found box right there. So next up, we just repeat this over and over. So step 3, the first row of the next column so the first row of the following column is how many units you need to get back to the value for the term. So here we have negative 2x cubed, we subtract another 4x cubed from it, and we get our negative 6x cubed. So we're good to go. So we just repeat this until we get to our lowest value. So we have right here, we need to find our missing x times the value gives us negative 4x cubed, so this is going to be negative 4x squared. 4x squared times x is negative 4x cubed. Keeping that in mind, we know that this guy down here is going to be negative 4x cubed. So negative 2 times negative 4x cubed, it's going to be 8x cubed. We know that we need to, we're at 8x cubed, or wait, whoa, 4x squared. So now we're at our squared terms. We know that we don't have any x's here. We can basically say, well, there's a plus 0x squared because there's none of them right here. So we need to figure out what we have to add to 8x squared in order to 0x squared. In this case, 8x squared minus 8x squared will get us to a 0x squared right here. We continue, knowing x times the value is going to give us negative 8x squared. Turns out that's minus 8x. So we bring this one down. We know it's negative 2 times negative 8 positive 16x, so we use the found width to calculate the missing area for our second box. Repeating over and over. So now we have the 16x. We know that we have to find whatever value is here so that they add up to 18x. So that's just going to be a plus 2x. Again, we figure out the missing value. So x times 2x, well, we need to multiply it by 2 in order to get this. So we have a plus 2. So we know that this length right here is also going to be a plus 2. Well, 2 times 2 is negative 4. And so finally what we have to do is kind of end it with step 3 here. So we have a negative 4, we want to get up to negative 1. So we know we need to add 3 in order to do that. So this is finally a plus 3. Because we're at the last column, we can't really multiply x by a value to get to 3. So what we do instead is call this the remainder. So this right here, let's do it in orange. The remainder is going to be this guy right here divided by our denominator. So this is going to be plus 3 divided by our x minus 2. Our final answer, our function can also be written as all of these blue parts. The x cubed minus the 4x squared minus 8x plus 2 plus our remainder divided by our divisor, or by our original numerator. So these two are saying the same exact thing. They're giving us the same exact information, or if we put some inputs in here, we're going to get the same exact outputs. And actually from this final term, you can start looking at those slant asymptotes. I'm going to do one more example to really lock this in. It's not going to be as long, but it'll give you a good idea of what we're doing. So for our next function, f of x is going to equal 6x squared minus x plus 3. Okay. 6x squared minus x plus 3, and we're going to divide that whole thing by 3x plus 1. So just like the last time, we're going to set up our answers. So we're going to put our 3x and our plus 1 as our width. We're going to try to find what this will simplify down to once we divide our numerator by our denominator. So I'm going to try to use the same exact colors here. So the first thing we want to do is get our first variable right down here. So we know that we're going to start off with the 6x squared, and we need to figure out what the missing width is right here. So 3x times a value equals 6x squared. You should know that that is equal to 2x. 3x times 2x is 6 times x, or 6x squared. And now we're going to bring that down to figure out the missing value here. So plus 1 times 2x, we are going to get a 2x down here. Next up, we got to figure out what our next value is. So we look up at this and we're saying, okay, well, we know our whole function So numerator is so we need to figure out what we need to add to 2x in order to get to a negative x, like so. So we know, well, 2x minus 3x will give us negative x, so this one is actually going to be minus 3x. We do the same exact step, just going back to this. 3x should turn into a negative 3x, so we know that this width has to be equal to negative 1. So we're following it right here, negative 1 right here. 1 times a negative 1 is going to give us a negative 1. And we know that this has to add up to, our negative 1 has to find a value so that it adds up to 3. Well, the difference between these two is 4. And so we're back down to our remainder. Because once again, 3x cannot multiply by anything to get to a 4 unless we have irrational number, or unless we have our rational values or functions. So here we again have our remainder. So all we do is add the remainder to the end and divide it by the denominator right here, 3x plus 1. So our final function in this case is going to be equal to 2x minus 1 plus 4 divided by 3x plus 1. There you have it. So these actually do correlate to these slant asymptotes. If you look at this denominator, this is actually going to give you the values. This is actually going to give you some interesting values, especially right here. This, if you put it into Desmos, will end up having some slant asymptotes. Turns out when your x gets really big, this is all what you're left with. So you can actually see what the equation is for your slant asymptote based off of our polynomial long division. So it's a different way of looking at the same function, but to get more information out of it.